So this diagram shows the typical FCC unit. So here you can see the different units as degenerator, then reactor, then fractionator, absorption, debutanizer and depropanizer. So debutanizer and depropanizer, they will separate the butane and propane separately. So here the feed will come, that is sent to the food as catalytic cracking, where it will be cracked again. So here you can see the steam is used in order to make the catalyst in flow motion. So the catalyst which is used, it is sent to the regenerator, and regenerator catalyst again sent to the riser, where it will again crack, and then cyclones they are kept to remove the catalyst fines. So when the cracked gas, it will come to the fractionator, where it will be fractionated into the gasolines and the heavy cycle, which is uncracked one. The lighter one which comes, that again separated or is taken into the absorption, where the C2 and nitric are separated, and the butane and the propane, that will be separated into this one. So here the butane will be removed first, and then the propane and the butane gas which is remaining, that will be separated out. So the next thing that we will see is the hydrotreating of the petroleum crude oil. So in hydrotreating, we are mainly the reaction with the hydrogen in order to separate it. So catalytic hydrotreating is the hydrogen process used to remove about 90% contaminant such as nitrogen, sulfur, oxygen and metals from liquid petroleum fractions. So if these contaminants are not removed from the petroleum fractions, they can have detrimental effects on equipments, catalysts and the quality of the finished product. Typically, hydrotreating is done prior to processes such as catalytic reforming, so that the catalyst is not contaminated by untreated feedstock. Hydrotreating is also used prior to catalytic cracking to reduce sulfur and improve product yields, and to upgrade middle distilled petroleum fractions into finished kerosene, diesel fuel and heating fuel oils. In addition, hydrotreating converts olefins and aromatics to saturated compounds. Now we'll see the catalytic hydrodesulfurization process. So as the name suggests, it's hydrodesulfurization. So sulfur will be removed. So hydrotreating for sulfur removal is called hydrodesulfurization. In a typical catalytic hydrodesulfurization unit, the feedstock is deaerated and mixed with hydrogen treated in a fired heater 315 to 425 degrees centigrade, and then charged under pressure, that is around 70 bar, through a vertical bed catalytic reactor. In the reactor, the sulfur and nitrogen compounds in the feedstock, they are converted into hydrogen sulfide and ammonia. The reaction products leave the reactor and after cooling to a low temperature enter a liquid gas separator. The hydrogen rich gas from the high pressure separation is recycled to combine with the feedstock, and the low pressure gas stream rich in hydrogen sulfide is sent to a gas treating unit where hydrogen sulfide is removed. So generally the sulfur is removed, which creates a problem in the refining processes. When the clean gas is then suitable as fuel for the refineries furnaces, the liquid stream is the product from hydrotreating and is normally sent to stripping column for removal of hydrogen sulfide and other undesirable components. In cases where steam is used for stripping, the product sent to vacuum dryer for the removal of water present in it, and hydrodesulfurized products are blended or used as catalytic reforming feedstock. So here is the flow sync of hydrotreating. So feed, it is sent to the furnace and then to the reactor. So here the hydrotreating will take place. Then it is sent to the hot HP, say hot high pressure separator. Then it is sent to the cold high pressure separator. So sour water will come. So sour water generally means it will have the sulfur content. The recycled gas that will send for the scrubbing, H2 is sent out after for the treatment, and the hydrogen which is untreated, that is sent back over here. So in reactor generally it is the hydrogen, the reaction will take with the hydrogen. So sulfur plus hydrogen, that will give the hydrogen disulfide. So here the sulfide removed gas that will come here. Then at a low pressure separator, it is sent to the stripper. In the stripper, the removal of the sulfur is the removed sulfur. Then we get the desulfurized product over here, and the other fraction that are C3 and more. So that we get as gas C3 components, and we can just set naphtha, which has a higher boiling fraction, and remaining esters, remaining gas we can send for the further sulfur recovery from it. So here treating with hydrogen to remove the sulfur, and then it is sent to have the products of the desulfurize the crude oil. Then in trickle bed reactor, so here if we can see the it is trickle bed reactor where gas liquid separation will take place. So catalyst bed, then we have the support grids, like we have the catalytic particle with the liquid film. So it should be completely wet in order to have the good mass transfer. And then we have the inner beds, and here with the gas liquid which is coming. So here is the deflector which will separate gas and liquid. So the gas will come around here, and the liquid which comes to the distributor, and it is distributed well around the bed. So then trickle bed reactor, the name suggests the trickling will occur. So the liquid which is separated, so it will trickle in the bed, and after the reaction is completed, the product we can remove from the product. So the liquid which should completely wet the particle in order to have the good mass transfer and good heat transfer, and the reaction will take place, and we can remove the product. So after hydrotreating processes, so it is other hydrotreating process, so it can also be done to improve the quality of pyrolysis gasoline, that is pi gas in short, or byproduct from the manufacturing of ethylene. Traditionally, the outlet for pi gas has been motor gasoline blending because of its high octane number. However, only small portion can be blended untreated owing to the unacceptable odor, color, gum forming tendencies of this material. The quality of pi gas, which is high in diolefin content, can be satisfactorily improved by hydrotreating, whereby conversion of diolefins into monoolefins provides an acceptable product for motor gas blending. The hydrotreating processes differ depending upon the feedstock available and catalyst used. Hydrotreating can be used to improve the burning characteristics of distillates such as kerosene by converting aromatics into naphthalenes, which are cleaner burning compounds. Lube oil hydrotreating uses hydrogen to improve product quality, with mild lube hydrotreating saturation of olefins and improvements in color, odor and acid nature of the oil are achieved. The operating temperature and pressure are usually below 315 degrees centigrade and 60 bar. Severe lube hydrotreating temperature is around 315 to 400, and hydrogen pressure up to 205 bar is capable of saturating aromatic rings along with sulfur and nitrogen removal to impart specific property not achieved in a mild condition. So after hydrotreating, the hydrocracking takes place, where we can crack the higher molecule into the low molecule. So it is a two-stage process, combined catalytic cracking and hydrogenation, wherein either feedstock is cracked in presence of hydrogen to remove more desirable products. So the process employs high pressure, high temperature, catalyst and hydrogen. The hydrocracking is used for feedstock that are difficult to process by either catalytic cracking or reforming. Since these feedstock are characterized usually by a high polycyclic aromatic content and or high concentrations of the two principal catalytic poisons like sulfur and nitrogen compounds, the process largely depends on the nature of feedstock and relative rates of two competitive reactions, hydrogenation and cracking. The heavy aromatic feedstock is converted into lighter products under wide range of very high pressures 70 to 140 bar, and fairly high temperature around 490 to 800 in the presence of the special catalyst. So generally hydrocracking, where it will crack the higher molecular weight into the lower molecular weight compounds. At the same time, it also removes the sulfur and nitrogen, which are the poisonous to the catalyst, and that may deactivate the catalyst which we are using in the processes. So after hydrotreating, hydrocracking becomes the one of the important. So when the feedstock has high paraffinic content, the primary function of hydrogen is to prevent the formation of polycyclic aromatic compounds. Another important role of hydrogen in the hydrocracking process is to reduce star formation and prevent buildup of coke on the catalyst. The hydrogenation also serves to convert sulfur and nitrogen compounds present in the feedstock to hydrogen sulfide and ammonia. The hydrocracking produces relatively large amounts of isobutane for alkylation feedstock and also performs isomerization for pour point control and smoke point control, both of which are important in high quality jet fuel. So if you consider the jet fuel, the pour point and the smoke point, the qualities we have to control. So to achieve that one, hydrocracking become one of the major refining processes to produce the jet oil for the jets. Then preheated feedstock is mixed with recycled hydrogen and sent to the first stage reactor, where a catalyst converts sulfur and nitrogen compounds to hydrogen sulfide and ammonia. Limited hydrocracking also occurs in this one. After the hydrocarbon leaves the first stage, it is cooled and liquefied and run through a separator. The hydrogen is recycled to the feedstock. The liquid is charged to a fractionator. The fractionator bottoms are again mixed with the hydrogen stream and charged to the second stage. Since this material has already been subjected to some hydrogenation, cracking and reforming in the first stage, the operation of the second stage are more severe and they will employ high temperature and pressures. Again, the second stage product is separated from hydrogen and charged to the fractionator. So here is the configuration for hydrocracking process. So this will show how we can separate the crude oil and how we can crack them and remove the unwanted components. So if you see the flow scheme, so the feed will come, then it is reacted with the hydrogen in the reactor, and after reacting with the hydrogen, the hydrocrack, so it will have the removal of ammonia and sulfur, hydrogen sulfide. Then the hydrocrack the oil, it will come to the fractionator where we can remove the C1 to C4 low distillate, then we can have the naphtha and we can remove the middle distillate. Whereas the low pressure step rate, they will come here and they will again react with hydrogen, and then again it is passed to removal of the C1 and C4. So the dark line, they will represent how the flow is occurring. So first is reacted with hydrogen, then crack, and then is separated to separate C1, C4 and naphtha and middle distillates. The high low pressure separated, they will again react with hydrogen and then again they will mix with the mainstream. Whereas the acid gas and the NH3, they are removed from this one. So acid gas is hydrogen sulfide and nitrogen, which are unwanted and poisonous, they will be removed over here, and hydrogen, which is unused, it is recycled back. And if you want, we can have the fresh hydrogen requirement. So here the hydrocracking, the feed is reacted with hydrogen to have the cracking, and also for the removal of the nitrogen and sulfur from the components. So catalytic reforming, if you have seen, then it is an important process used to convert low octane naphtha into high octane gasoline blending components called reformates. So reforming the total effect of numerous reactions such as cracking, polymerization, dehydrogenation and isomerization taking place simultaneously, and depend upon the properties of naphtha feedstock as measured by the paraffin, olefin, naphthalene aromatic content and catalyst use. Reformates can be produced with very high concentrations of benzene, toluene, xylene and other aromatics useful in gasoline blending and petrochemical processing. Hydrogen, a significant byproduct, is separated from the reformate for recycling and used in the other process. So reforming, if you say, so that the name suggests the products are reformed. So isomerization, where we can have the isomerate, then cyclization, where the stretch compound into the cyclic one. So this is the endothermic reaction. In aromatization, the cyclic components, we can, after the dehydrogenation, we can convert them into the aromatic ring, and the combination, where we can use the two or more processes simultaneously. So in this one, the carbon is removed from the carbon is added from the side chain to have the cyclic ring of the 6 carbon content, and then we can have this benzene ring after removal of the hydrogen. So these are the different kinds: isomerization, cyclization, aromatization, and the combination of any 2 or 3 of the processes in order to get the reforming. So reforming will it will make us to get the desired composition in the product. So generally, the catalog reforming feedstock and the product analysis volume percentage. Then alkane, the feed will have the 45 to 55 volume percentage. Then product will have 30 to 50. Alkene 0 to 2 we can achieve for 0. Naphthenes we can reduce to 5 to 10. And aromatics 45 to 60 volume percent we can reform it. So catalytic reforming comprises a reactor and product recovery section. So there is a feed separation section comprising a combination of hydrotreatment and distillation. Most processes are platinum as the active catalyst. Sometimes platinum is combined with the second catalyst. Bimetallic catalysts such as rhenium and or another noble metal. There are many different commercial processes including platforming, power forming, ultraforming, and thermoform catalytic reforming. Some reformers operate at low pressures 3 to 13 bar, others at high pressures up to 70 bar. Some systems continuously regenerate the catalyst in other systems. One reactor at a time is taken off stream for catalyst regeneration, and some facilities regenerate all the reactors during turnarounds. In the platforming process, the first step is preparation of the naphtha feed to remove impurities from the naphtha and reduce catalyst degradation. The naphtha feedstock is then mixed with hydrogen vaporized and passed through a series of alternating furnace and mixed bed reactors containing platinum catalyst. The effluent from the last reactor is cooled and sent to the separator to permit removal of the hydrogen-rich gas stream from the top of the separator for recycling. The liquid product from the bottom of the separator is sent to a fractionator called stabilizer. It makes the bottom product called reformate. Butanes and lighter go overhead are sent to the saturated glass plant. Then feedstock, they comes to the reactor. Then they are sent to the furnace. In reactor, the catalytic reforming takes place, where the product will be reformed into the different. So it may be multiple stage reforming section, where we can use combination of one or more techniques. Then separator will separate the reformed product and the unreformed product, and the unused hydrogen we can have for the recyclation. Then the product will consist of many components which are formed during the reforming. So the fractional will separate them into the reformate which are reformed and the light hydrocarbons. Semi-regenerative catalytic reforming will have the reformate in desired quantity and the unreformates. So here you can see the different stages at different temperature. So the reformation taking place of desired level, and after reformation taking place, the product are removed. So reformate and the other components, they are removed in the stabilizer. In continuous regenerative reformings, here you can see the product which is desulfurized taking place, and they will go with the series of the reactors where reforming is taking place, and the unreform is sent back to the reactor again. So that will ensure the complete reformation technique, and also the volume percentage of the reformate is also high. So here we can achieve for the greater efficiency and the greater yield of the reforming process. So here the catalytic reforming reactors will have the axial flow reactor, where the flow is axial one, and the radial flow reactor where the flow will be radial or from outside to inside. There is an axial from up to bottom, so they will pass through the catalyst bed, and the catalyst bed the reformation will take place. The next comes is the alkylation. So here is the reaction in order to get the alkyl. So it is a combination of low molecular weight olefins, primarily a mixture of propylene and butylene, with isobutene in the presence of a catalyst, either sulfuric acid or hydrofluoric acid. The product is called alkylate and is composed of a mixture of high octane branch and paraffinic hydrocarbons. Alkylate is a premium bending stock because it has exceptional anti-knock characteristics and it is clean burning. The octane number of the alkylate depends mainly upon the kind of olefins used and upon operating conditions. Sulfuric acid alkylation process, if we consider, then the sulfuric acid is used. So in the cascade type sulfuric acid, alkylation is the feedstock. Propylene, butylene, amylene and fresh isobutane enters the reactor and contacts the concentrated sulfuric acid catalyst in concentration of 85 to 95% for good operation and to minimize corrosion. The reactor is divided into zones with olefins piped through distributor to each zone. The sulfuric acid and isobutane flowing over baffles from zone to zone. The reactor plant is separated into hydrocarbon and acid phases in a settler, and the acid is returned to the reactor. The hydrocarbon phase is hot water wash with caustic for pH control before being successively depropanized, deisobutanized and debutanized. The alkylate obtained from the deisobutanizer can then go directly to motor fuel blending or be rerun to produce aviation grade blending stock. The isobutane is recycled to the feed. So here is the process. So feedstock, it will come to the reactor, then it will move to the acid settler, then caustic is added. So caustic scrubber is removed in scrubber, then debutanizer will remove the butane and isobutane, then it will recycle back, and the alkylate which will get. So alkylate is mainly done to increase the octane number of the component, and octane is necessary in order to improve the antenna properties. So octane number is a major property for a fuel. So generally earlier lead was added in order to get high octane number, but because of the environmental concern the lead is not added. So if you go at a petroleum pump where you see the unleaded petrol, so that makes you ensure that lead is not there in order to improve the octane number, whereas the branch chain molecules are added in order to obtain the more octane number.